All right, good morning, everybody. 10 o'clock, snowy day. Welcome back to your favorite class. Yes. All right, announcements. We're going to continue torsion of thin and non-circular members today in class. Hopefully we finish the lecture notes today. If we don't finish them, we're going to finish. Okay, so other announcements is homework 6 has been posted on strain transformations. I think that's due Wednesday. Is it due Wednesday? Yeah, Wednesday. I'm getting confirmations from the audience. Like they've actually looked at it. I'm just kidding. Right, and then your lab today, you'll have non-circular torsion lab this week. So Tuesday, Thursday, we'll have our sort of normal lab section, and this will be the last lab for the quarter. All right, so 4 labs in total for this class. This will be the last one. It'll be a lot like the first lab that we did for circular torsion, except we're going to be loading a rectangular bar instead of a circular bar. So you get to see some differences there between lab number 1 and the non-circular torsion lab, which we're going to do this week. So I'll get the information posted to Blackboard so you can sort of take a look at things. All right, how do we like the mean today? It took him a couple bites. Clever. Okay. All right, let's get back to where we were. Let me open a new tab here. All right, so last time we were talking about torsion of circular and non-circular members. And I'll just kind of bring in the PowerPoint slides and kind of start from there and just review kind of what we did. So last time we talked about torsion of circular members, sort of where the derivation of TL on GJ comes from for angle of twist, and the shear stress tau being TC on J. So we sort of talked about these things with the derivation. Here's a little bit more detail in the notes if you want to sort of dive into it. And we showed what a member with non-constant torque and non-constant polar moment of inertia might look like, right? So we had a general expression here for angle of twist given some non-constant torque or polar moment of inertia. And, you might see a homework problem like that coming up on the next set, so be aware of that. And then we talked about what the torsion of non-circular shafts might look like. And I sort of glossed over this by saying that the derivation of the shear stress and the angle of twist for bodies with non-circular cross sections, complicated. Oh my gosh. I had a question on my PhD qualifying exam about a circular shaft with a keyway in it, and it made me cry. Okay. I didn't actually cry, but I internally cried, and then I did the problem and it was okay. But it's complicated. All right. So we don't actually go through the derivation of the shear stress distributions and let's say a square cross section, a triangular cross section, elliptical cross section that's in torsion. We sort of kind of gloss over the derivation and say that, okay, the best we kind of want to do for this class is just say, where's the maximum shear stress going to occur if we are torquing this cross section, and what angle of twist would we expect in this cross section if we do have that torsion on our member. And so there's lots of charts and people have done these derivations. And so I'm kind of giving you a series of tables, both in your sort of equation sheet for this class and also on this note sheet, that sort of shows you where the maximum shear stress will occur. So here, like these black dots, and what the associated maximum shear stress is, and what the angle of twist is that you might anticipate given some certain torque on the piece. So that's about where we were last time. I showed that there was all these crazy like tomes. I'm not joking when I say like tomes of information about various cross sections and the derivations of angle of twist and shear stress on crazy looking cross sections like a double keyed shaft, or the plus sign here. I don't know if you want to call this the first aid sign. I don't really know what you want to call this cross section, but you get the idea. There's tomes filled with information regarding max shear stress and angle of twist for a variety of different cross sections. Okay, and so when we left off, we said that we were going to work through this example problem, relatively straightforward example problem. So I'll give you a second if you want to copy this down. And we here have a triangular cross section with dimensions given, 4 feet long, 1.5 inch for the side of an equilateral triangle, and it's under some torsion. We're told it's made out of aluminum 6061. And we want to determine the largest torque that can be applied if we have some maximum allowable shear stress and some maximum rotation angle that we can allow. All right, so we're going to check both of these things and see which torque would sort of run into a problem first, whether we have a problem with the maximum angle of twist or the maximum shear stress first, and which torque would get us to that location. So I'll give you a second here, and then we'll work through it. If you haven't registered to vote, for the love of all that is holy, please register to vote and go vote if you haven't done so already. I got my absentee ballot in the mail like 3 weeks ago. The next day, I brought it to City Hall. Okay, so vote. I'm getting like 14 text messages a day. Like, do you guys get text messages where it's like, oh my gosh, it's driving me crazy. Like, I want to be polite, but at the same time, I'm like, you've texted me 47 times in the last 2 weeks, and I've told you already that I've finished voting. Like, leave me alone. God. With that said, I'm going to constantly hound you guys to vote. Okay, enough waxing idiotic. Let's I'll bring the relevant information in and we'll work through this. All right, so here we go with an example problem. So here we have this triangular shaft. We're given dimensions of the shaft, 4 feet long, not 4 inches long. Equilateral triangle, some torque. We're told that it's made of aluminum. 6061 with the shear modulus, which is 3.7 MSI. All right. We're told that the maximum shear stress that this particular piece can withstand is 8 KSI. And the maximum angle of twist that we can handle, we'll call this phi max, is 0.02 radians. All right, so we want to find the maximum torque that we can handle in this cross section before it reaches one of these two sort of failure criteria, quote unquote. Okay, so there's a couple of places where you can go, but what we're going to want to do is we're going to want to sort of calculate what torque is required to get us to the max shear, calculate what torque is required to get us to this max angle of twist, and then take the lesser of the two values as our answer for the problem. Okay, so let's do that. All right, so for triangular member, since we have this equilateral triangle, we can sort of go to that chart that I showed before. Let's just pop that in really quick, just as a reminder. So here's a kind of the chart that you want to go to for an equilateral triangle cross section, which is sort of here, with side length A. The maximum shear stress occurs at these like long edges of the triangle, and it's going to be equal in value to 20 times the torque divided by A cubed. And the angle of twist associated is 46 times the torque times the length of the shaft divided by this dimension A to the 4th times the shear modulus G. Just what you would expect. Okay. So let's write those down here. We know that tau max from that chart is going to be 20 T over A cubed. And we have that our maximum angle of twist, given in radians, is 46 TL over A to the 4th G. Looks like I have a question in L chat. Voted last week, took 5 minutes. Excellent. Convince your colleagues to do the same. Oh, all right. So we're going to kind of work these more or less simultaneously. This is the maximum angle of twist. So we want to rearrange these guys to sort of solve for the torque that would cause these maximum shear stresses or this maximum angle of twist. So we can sort of think about rearranging this to be something like the max torque that we could handle, if we sort of rearrange this, is the max shear stress times a cubed over 20. Could sort of go through the same process over here with the angle of twist. The max that you could handle before you failed by the angle of twist criteria is like phi max a to the 4th g over 46L. So we'll sort of solve for both of these, and whichever one is less, that's the one that we're going to hit first for our sort of failure criteria. All right. So let's go. Here, my maximum shear stress is given as 8 KSI. The value of A given in the problem, 1.5 inches. Here, cubed, all over 20. Plug in values over here too. Maximum angle of twist, always given in radians here, 0.02 radians. Rad. Times 1.5 inches to the 4th, times the shear modulus, 3.7 MSI. All over 46 times my length. I was told that this is 4 feet, so I'm just going to work in inches here. 4 times 12. Anyone got a calculator? I'm just kidding. It's 48 inches. Did that one in my head. What's up? Okay, so if we work on the left-hand side here for maximum shear stress, this will be 600 inch-pounds. Over here, sort of punching everything into your calculator, 170 inch-pounds. All right. So if all we cared about was the maximum shear criteria given for the problem, then our answer would be 600 inch-pounds. Okay, but we're given this other criteria about the angle of twist. And so since we care about reaching the angle of twist too, which is this 0.02 radians, we're going to take this as our answer because we're going to reach that failure criteria for the max angle of twist first. So here will be your answer, 170 inch-pounds, and we'll say controlled by your phi max criteria. Okay. Questions? Nope. Okay. I think that one's pretty straightforward. Exclamation mark. Rar. Controlled by phi max. Phi phi fo fum max. All right. So that is torsion of non-circular members. Another thing that we need to talk about, which is sort of equally complicated, is torsion of thin-walled members. So that's going to be the next topic for the class. Okay. And we generally separate torsion of thin-walled members into open and closed cross sections. Okay. An open section might be, I don't know if we wanted to give some examples here. I'll try to stick with some from your book. Some open cross sections might be like a very thin rectangular cross section. All right. How about like a C channel? All right. How about a slotted circular cross section? Always a fun one. Okay, these would all be considered open cross sections. All right, there's no like enclosed area contained in any of these sort of cross sections. Right? So closed would be sort of the opposite of that. And a closed cross section would have some sort of area enclosed within the thin walls. So that would be one example of like a closed square cross section. Obviously a thin-walled circular tube, that's obviously pretty straightforward, going to be a closed cross section. So you get the general idea. There's some like enclosed area here. Okay. So we should maybe take a second to sort of like define thin-walled. I would say if the wall thickness is less than, let's say, 10% of the sort of like hydraulic diameter, that would be an appropriate value. So thin wall, it's like wall thickness is less than, let's say, 10% of hydraulic diameter. Have you guys talked about the term hydraulic diameter in any of your classes so far? Oh, maybe I shouldn't use this term then. Of longest cross-section dimension. Let's say that. When you get to your fluids class, you will learn about the hydraulic diameter. So let's leave that one alone for now. Okay, so let's first start with open cross sections. It shouldn't be open cross sections. It should be open cross sections. Okay, sorry about that. Open cross sections. All right. Again, we're going to kind of gloss over the derivation for time reasons and math reasons. Okay, so no derivation. We'll just sort of give you the equations here. Okay, so let's consider open section. And we're going to have to define some variables here, but I'll write the equation and then we'll define the variables. All right. So here, generally, the shear stress in this open section is going to be something like G phi times C. This is a little c over capital L. This is also going to be equal to 3 times the torque that you apply divided by this variable here. This is a zeta. I'd have to practice that one a little bit. Times c squared. All right. This is your most general expression for open cross sections. So we're going to have to define some of these terms, right? Whoa. And we'll define some of these terms. I think the best way to do it is kind of drawing a cross section and sort of maybe labeling a cross section. So let's look at a C cross section. And so what I mean is something that maybe looks like this. Okay, so it's like C-channel cross-section. All right, pretty obvious here. This tau here is going to be shear stress. G shear modulus. Phi, angle of twist in radians. Pull this over. Nope, that's as far as it goes. Seriously? I can't get rid of that? That's annoying. Capital T is the torque. L is the length of the shaft. And then we have these two variables that we haven't really seen before for torque, which is zeta and little c. So little c here is the wall thickness. Why they didn't use T, I don't know. It's sort of established that little c for thin cross sections is the way to go. I don't get it, but that's what it is. Okay, so wall thickness. And then finally this term zeta. Zoltan. Okay. Anyone know what movie? Zoltan. No? Come on. Dude, where's my car? It's like Ashton Kutcher's best movie. All right. This zeta term, this is what's called the median line length. Zoltan. The median line length is sort of what it says that it is. It's the length of the line that defines the middle of the thickness of the cross section throughout the entire cross section. What do I mean by that? All right, well, if we looked at the C channel cross section here, obviously like the wall thickness we've already sort of defined as the variable little c. But the median line is the line that sort of defines this particular line here, which is a line that runs sort of between the wall thickness throughout the entire piece. So this is the median line. Okay. The length of this line is the variable zeta. So depending on your open cross section, you're going to have a different value of zeta, obviously. And so some cross sections that you might want to look at or think about this variable zeta might be some examples that look like this. This comes from your Shigley book. And this picture is also in the notes. So you can sort of take a look at that, right? So for kind of like this just straight thin rectangular cross section, obviously C is just the thickness of this cross section and zeta is this length, all right? But in the circular cross section, zeta here would be something like, oh, terrible zeta, terrible, I say. Is going to be something like 2 pi r, right? So it's like this whole length around the circumference of the piece, where r would be the distance to the center here of the thickness of the wall, all right? Obviously, this would be your zeta here. For an L bracket, it's this length here. For a Z bracket, something like that. Okay, so you get the idea. Each one of these has its own sort of definition of zeta. So why don't we try a practice problem looking at one of these thin-walled structures. And we'll do that now. All right. 12-inch long strip of steel is an 1/8 inch thick and 1 inch wide. See allowable shear stress 11.5 KSI. Find the maximum allowable torque and corresponding angle of twist in degrees. Okay. This one should be pretty straightforward. It's just kind of like plug and chug here. It's kind of an easy part of the class, to be honest. So let's do this. So here we have an example. I'll just draw the cross section. Got a strip of steel. Tells us it's sort of 1 inch wide, and it's an 1/8 inch thick, and it goes back into the page a certain amount. Okay. So we're told that this is 12 inches into the page. Not to scale, BTW. This is 1 inch in width. And we're told that it has a thickness of 1/8 inch. So we're told that if we have some maximum shear stress, which is 11.5 KSI, that we want to find the maximum torque that it can handle and the corresponding angle of twist. So find Tmax and the angle of twist at Tmax. And we're also told that the shear modulus for this particular piece is 11.5 MSI. All right, well, we have a series of equations that we're just going to kind of plug and chug here for this. The first is that our shear stress here is this 3T on zeta C squared. This is kind of where we're going to start. Remind yourself what this zeta variable is. Here it's the median line length. So we can sort of draw our median line in here. And this problem, it's pretty easy to see that zeta is going to be 1 inch. For L brackets and Z brackets, it can be a little bit more confusing when you're talking about like calculating, some half thickness as you go around a bend or whatever. But this, just flat piece of material is pretty easy to see what's going on here. All right. So we could rearrange this. We kind of want to solve for the torque. So we could see that Tmax here is going to be something like tau max times this zeta value times C squared all over 3. We can plug some numbers in here. Tau max 11.5 KSI. This zeta value is 1 inch. It's kind of the same as sort of the width of the plate, or the width of the thin piece here. And then C is the wall thickness. It's 1/8 inch squared. This all here over 3. And we'll get that the max torque is going to be 60 inch-pounds. I mean, this is not a very large value. You think about this. Okay, 60 inch-pounds. All right, so if you got a 6-pound weight, you hold that 10 inches away from the edge of this cross section, you hold the 6-pound weight on the end of there. That's it. That's all that this guy can handle. All right, he's going to start failing at that point. So you got this like pretty strong piece of steel here. You know, you consider steel a pretty strong piece. If it's an eighth inch thick, you're going to torque this thing. It can't really handle very much. All right, open cross sections, not so good in torsion. All right, just telling you. All right, now we can use this value to find the max angle of twist. And again, you're going to want to use another one of the equations that I gave here, but sort of the other equation of this form. It's going to be G phi C on L. Can rearrange this for your phi. All right, tau max here again, 11.5 KSI. The length into the page we were given as 12 inches. G, that's your shear modulus. It was given to us in the problem, 11.5 MSI. How convenient that those two things will approximately cancel. And times C, which is 1/8 inch. All right, so this angle of twist, you can handle 0.096 radians. We're asked for the answer in degrees. So multiply by 180 on pi, you're going to get 5.5 degrees. All right, so that's your angle of twist at sort of the maximum shear stress for this problem. Cool. That's, I mean, pretty hefty. That's a physically noticeable rotation angle, right? All right, last thing we want to talk about is closed cross sections. And this will kind of finish up your thin-walled torsion notes. Okay, so again, thin-walled structure. So, you know, the thickness of the structure, much, much less than sort of the maximum dimension. Okay, so let's say the thickness is much, much less than D, where D is some dimension of the cross section. We'll say like 10% max. Even though we just did a problem that was 12.5%, don't tell the professor. All right. Closed wall sections must enclose some area that is not, you know, filled with air or something. Right? So must have an enclosed area. All right. So maybe you have some wonky looking cross section that looks like this, and it's thin walled border. Okay, sure. That's a thin walled structure with some closed cross section, where this is like an enclosed cross section. Okay. So an enclosed area. This enclosed area here is given the variable a sub m. I don't know why m, but that's just the general nomenclature. If you got a problem, take it up with Newton. Not Fig Newton, like the scientist guy. Okay. All right, so again, without derivation, we have the following relationships. The shear stress is the torque divided by 2 AM times T. It's equation number 1. Now we're back to using little t for reasons I don't know. And your angle of twist phi is T. That pesky zeta coming in again. L all over 4G. Not 5G, 4G. AM squared T. All right, where we're going to define these guys. Tau you know, T you know. The only things we really need to define here are AM is the enclosed area. This little t, wall thickness. Zeta again is your median line length. Same sort of definition we had for the open cross section. And everything else you kind of know on here. So no real need to sort of define everything else again. 4, 1 more than 3, 1 less than 5. There, I defined it for you. In case you were curious. All right, so since we're not doing derivation, let's just cap it off with one more example problem and we'll get you out of here. Got a steel tube, 40 inches long, 1/8 inch wall thickness, 2.5 by 3.6 inches rectangular cross section. That's outer dimensions of the cross section. The allowable shear stress 11.5 KSI. Estimate the allowable torque and the angle of twist. I think one of the more frustrating things about the election coming up is that we're definitely not going to know the winner the day of, like in previous elections. It's going to be man, it's going to be a long, like 2 weeks, I got to tell you. They're going to have to count all the mail-in votes. Some states can't even count their mail-in votes until election day, which is a weird rule, but is the rule. Wisconsin is one of those states, by the way, where they can't open the ballots that are mailed in until election day. And Wisconsin's generally a swing state. Man, it's going to be a contentious situation. Okay. Let's get down to business with this example problem. All right, so let's draw a picture of our cross section. We've got this rectangular cross section. I'm going to sort of not draw this to scale, exaggerate the wall thickness a bit here. And just into the page. As such, we're told that the outer dimensions here are 2.5 by 3.6. Okay. And that our wall thickness here is 1/8 inch. All right. So one thing we might want to draw or define right away is this median line length. So again, that's this sort of rectangle that's contained by the midline of the wall thickness here. So this is the line that defines xi. This also defines AM. Okay, it's not actually the area that's enclosed by the rectangle, it's the area enclosed by the median line. Just to be clear about that. I wasn't entirely clear about that before, so apologies for that. AM is the area enclosed by the median line. Okay, so we want to find what is the torque that this thing can handle, given that we have tau max is 11.5 KSI. Our shear modulus G is 11.5 MSI. And the length of the shaft was also given as 40 inches. Okay, we want to find the maximum torque that we can handle and the angle of twist at T max. Okay, so let's do this. First thing we're going to want to define is this variable zeta. This is the total sort of length of this line here. It's basically like the perimeter of this like internal rectangle. So I have this total side length here is 2.5 inches. So one side length here is 2.5 inches minus 1/8 inch. Okay. And I'm going to add to that sort of the same thing on the next side length. So that would be like this little piece here. And all of this gets multiplied by 2. So this is giving me my full perimeter. So this here will be 11.7 inches. I also might want to define this area enclosed by the median line. And that's going to be very similar looking, except not perimeter here. We want area. So this is going to be like 2.5 inches minus 1/8 inch. Multiplied by that other sort of side length, 3.6 inches minus 1/8 inch. Here I'll get a median area, which is 8.25 square inches. Okay, so I'm kind of ready now to tackle or just input the equations directly. So let's go ahead and do that. So kind of the equation that we wrote here is that the shear stress is the torque divided by 2 AMT. Or we want to rearrange this to solve for maximum torque. So this will be that this maximum torque is simply going to be 2 times tau max AMT. And put numbers in here. Tau max is 11.5 kip. AM we solve for 8.25 inches squared. And then our wall thickness here, 1/8 inch. Do the hokey pokey. Turn yourself around. T max 23.7 kip inch. Markedly higher than we saw for the thin structure. Now we have a little bit larger dimensions here, but you know, this is like 10,000 times stronger than what we saw the other way. 1,000 times stronger, roughly. We also want to solve for this maximum angle of twist. It's going to use our sort of max torque. And we saw the equation here was T max zeta, that funky variable, over L, divided by 4G AM squared T. All right, so we can just start plugging stuff in here. Our max torque, 23.7 kip inch. Oh God. Our value of zeta we kind of solved for before, 11.7 inches. The length of this shaft was given to me, 40 inches. This is all my numerator here. Over my denominator, 4 times the shear modulus, 11.5 MSI. Times my median area squared, which is 8.25 inches squared. Multiplied by the wall thickness of 1/8 inch. All right. Remember, your value is going to come out from this equation in radians. All right. You work this 0.0283 radians. Or if you want it in degrees, which I think is just kind of a little bit more well understood, this is going to be 1.62 degrees. All right, so we saw this closed steel cross section with a torque of 23.7 kip inch, only rotate 1.6 degrees. The open thin walled structure that we saw that only had like 60 inch pounds, 60 inch pounds? Yeah, 60 inch pounds on it. That rotated 5.5 degrees. So in short, and you will see this when you kind of attack your homework coming up, Open structures, horrible in torsion. Horrible, right? So last comment here. Open-walled structures. Horrible in torsion. If you have experience or have maybe seen this before, compare mentally these two cross sections. Sorry for the rushed picture. But just think about in your head, if you had the same materials and you were going to put both of those guys into torsion, which one's going to hold up better? Which one's going to have a higher angle of twist when you torque it? Which one's a better structural material? It better be number 2 in your head, right? So you'll do a homework problem where you actually look at the relative amounts of torque that these two cross sections can handle before they fail, and you'll see a really big difference. Okay, 2 minutes over. Sorry for that. This closes the thin-walled and non-circular cross-section notes. We'll start in pressure vessels on Wednesday. So long.